Conventional, here you see student what are written. A convenient method to describe the magnetic field around the magnet is to draw the magnetic field line around it. In order to do so, place a magnet on the cardboard sheet and gently sprinkle some iron filling uniformly over it. The iron fillings are found to arrange themselves in a pattern shown in the figure 2.2 Agastrom. 2.2. So how this pattern, when two iron fillings arrange themselves, okay, why two iron filling arrange themselves in definite pattern? This is due to the reason that each piece of iron filling becomes a small magnet and experience a force in a certain direction in a magnetic field due to the magnet. These curved path along which the iron fillings arrange themselves due to the force acting on them in the magnetic field of the bar magnet are called the magnetic field line. If the position of the magnet is changed, the magnetic arrangement of the iron fillings also change. Tracing or mapping magnetic field due to bar magnet using compass. To trace the magnetic field due to bar magnet, fix a paper sheet on a drawing board by means of the bar pins. Place a bar magnet on the sheet and mark its boundary with a fine pencil. Now place a small compass needle close to the south pole of the magnet and mark two pencil dots exactly at the two end of the needle. Note that the north pole end of the needle represented by arrow, you know, represented by arrow in the being attracted by the south pole of the magnet. Move move the compass in such a manner that one in north pole of the needle coincide with the second pencil dot marks the position of the other end of the pole needle with a dot. Repeat this process of moving the needle and marking dots at its two end till its south pole reaches the north pole of the magnet. Obtain a smooth curve by joining the various dots. This smooth curve represents magnetic field line. Repeat the above procedure from the same pole of the magnet but from the different point near to it and trace our magnetic field lines in similar fashion. To indicate the direction of each magnetic field line, mark an arrow on it from north pole to south pole of the magnet as shown in figure 2.2. This is the direction which a north pole would follow while going along the field line. So these are there. Now let us try to understand, student, magnetic field line. A magnetic field line is directed from the north pole to south pole outside the magnet. A magnetic field line is closed and continuous curve. We have not shown magnetic field line inside the magnet where these directed from the south to north. The magnetic field lines are curved near to the pole where the magnetic field line is strong and are apart near the middle of the magnet and far from magnet the magnetic field is weak. The magnetic field lines never intersect each other because if they do so there would be two different directions of magnetic field at the point which is observed. In case of field lines are parallel uh, equidistant, this represent a uniform magnetic field. The earth magnetic field is uniform in a limited space. So this is what. Observe the direct discovery experimental evidence or a relation between the electricity and magnetism. For many years, it was thought that electricity and magnetism have no relationship with each other. The first evidence that there exists such a relationship between the two was observed in 1820 by Hans Carries, professor of physics, Copenhagen, the man who himself used to demonstrate that electricity and magnetism had no relationship with each other. He used to do so by pencil a current carrying conductor XY directed both magnetic needle north and south, but perpendicular to the axis of the needle, shown that the magnetic needle did not move. But one day, what happened took place? The current carrying conductor parallel to the axis of the needle, and the needle was the deflected, which was much against the experience. On reversing the direction of the current, the needle moved in the opposite direction on the further investigation. Oersted found that the direction of the deflection of the needle depend not only on the direction of the current but also on whether the conductor was above or below the needle. Thus, a great discovery in the history of electricity and magnetism was made purely by the accident. Okay, Lawrence once said, "Such accident come only to those who deserve them." The experiment was shown. So this is the freely suspended needle, north south. Conductor perpendicular to the needle, north south. Now what happened? Conductor above needle. So when the conductor are there, here this one, the needle north south. Okay. Now the conductor changed, so the direction of needle also deflected. Conductor below needle. The Oersted experiments demonstrate around every conductor carrying an electric current there is magnetic field. In other words, we can produce magnetism from the electric current. Later on, Andrew Morin Ampere, the French mathematician and physics, gave rule called Ampere's swimming rule for finding direction of or deflection of the needle due to the magnetic field current. Let us observe, imagine himself to be swimming alone, the conductor in the direction of the current and facing the magnetic needle. Then the north pole of the needle will deflect towards his left. Magnetic field due to current carrying straight conductor.